Okay, this is part 2 of section 10.14. We're going to, in this video, we're going to define the Maclaurin series as just the Taylor series expanded about x equals 0. Then we're going to use that to define or to show you the Taylor or the Maclaurin series expansion for 1 over 1 minus x, for cosine x, for e to the x. Then I'm going to leave it to you to find the Maclaurin series for sine x. But what's really neat about this is we can write all of these functions. We've already seen the geometric series 1 over 1 minus x is represented, or 1 over 1 minus x is equal to the geometric series 1 plus x squared plus so on and so forth. We've already seen that, but we're going to show you another way to get it using this Maclaurin series. You're going to see that you can write as a series of polynomial terms an infinite series. You can expand cosine x, sine x, and e to the x. And that's really awesome, and that's how your calculator is used to calculate values for those functions. Instead of just storing an infinite number of values, they actually use these infinite series to come up with values and estimates for those. So first, let's define the Maclaurin series. It's just the Taylor series for the function, but it's expanded about x equals 0. You might remember from the Taylor series how we defined it a little while ago. We call it the Taylor series. For f of x is equal to the series for n equals 0 to infinity of the nth derivative evaluated at some center a times x minus a to the nth power over n factorial. But if we evaluate that at 0, we get the Maclaurin series. This is a special case of the Taylor series. N equals 0 to infinity. The nth derivative of f, this time evaluated at 0. And x minus 0 to the nth power is just x to the nth power, still over n factorial. Now, we did ln x a little while ago, or on the last video, but we can't create the Maclaurin series for ln x since 0 is not in the domain. So we can't find f of 0, so we can't expand it about that point. Remember, the Taylor series is created off of a point known to be on the function value. That's why we expanded that using the Taylor series in the last video about x equals 1, because that's a point we know the value for ln 1. So when we do the Maclaurin series, it'll only work for functions that are defined at 0 and continuous at 0. So let's take a look at this, and let's see what we can do with this geometric series that we already know. We showed this just using simple division the other day, is equal to 1 plus x, plus x squared, plus x cubed, plus dot, 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 and just keeps going and going and going. And remember, this series is convergent for values of x between negative 1 and 1, not including negative 1 and 1. If x was equal to negative 1, and this would be the alternating series 1 minus 1 plus 1 minus 1 plus 1. It would alternate between the values of the nth partial sums would alternate between the values of 1 and 0, so it doesn't converge to a single point. And we can't say the limit of the nth terms is 0, so we know by the nth term divergence test that this series diverges for a value of x equals negative 1 or x equals 1, and so it's only convergent for values between negative 1 and 1. But let's look at this using this Maclaurin series. Remember, to do this, we need to find f of 0, which is obviously 1. We need to find f prime of 0, f double prime of 0. Let's see if we can establish a pattern by the time we get to the third derivative evaluated at 0. So let's take a look, and let's say this is also equal to, let's look at the function f of x equals 1 minus x raised to the negative 1 power. So f prime of x is equal to negative 1 times 1 minus x to the negative 2 power. But remember the chain rule, we have to multiply by the negative, the derivative of what's inside. So negative 1 times that will make this a positive 1. So this just simply equals 1 over 1 minus x squared. And let's do the same thing for f double prime of x. Let's go here. This is just 1 out front. So this is equal to negative 2 times 1 minus x to the negative 3. Again, multiply by chain rule and get plus 2 times 1 minus x to the negative 3, which is 1 over 1 minus x cubed. Remember, that changes the positive because of the chain rule. We had to multiply by that derivative of what's inside. Let's go ahead and do the third derivative. And we'll see it's going to be negative 6 times 1 minus x to the negative 4. Again, times the chain rule, negative 1 is the derivative of the inside, so it's going to multiply this to make positive. So it's going to end up being, oh, this was 2, sorry. This is equal to 6 over 1 minus x to the 4th power. So let's evaluate these. F prime of 0 is just 1 over, when we plug in 0 for x, we get 1 over 1. F double prime of 0 is going to be 2. We plug in 0 here, we get 2 over 1, so we get 2. F triple prime of 0, plug in 0 here, we get 6 over 1, or just 6. Now what I want you to see is this is equal to 0 factorial. This is equal to 1 factorial, sorry. This is equal to 2 factorial. This is equal to 3 factorial. Let's go ahead and do the fourth derivative, and let's just see if this pattern continues. This would be negative 24 times 1 minus x to the negative 5. And then we multiply the derivative of the inside because of the chain rule to get positive 24. So that's going to equal 24 over 1 minus x to the 5th. 24 is 4 factorial. So the fourth derivative, evaluated at 0, would also be 4 factorial. So it looks like this pattern continues. So we can say that the Maclaurin series for the geometric series here, 1 over 1 minus x, is equal to, now remember this is going to be f of 0 plus f prime of 0 plus f double prime of 0. Oh, this is times x, sorry. This is going to be f double prime of 0 times x squared over 2 factorial. And this is going to be plus the third derivative, evaluate at 0 times x cubed over 3 factorial plus the fourth derivative, evaluate at 0 times x to the 4th, 4 factorial. But remember, this is just f of 0 was 1. F prime of 0, this is times x here. F prime of 0 is just 1, so this becomes plus x. F double prime of 0 is 2 factorial. So 2 factorial over 2 factorial cancels. That leaves me just x squared. F3, the third derivative of f, evaluate at 0, was 3 factorial. So this leaves me with x cubed plus x to the 4th plus dot, dot, dot. So we use the Maclaurin series there to show what we already knew from division when we first encountered the geometric series, is that 1 over 1 minus x is equal to the infinite series 1 plus x squared plus x cubed plus x to the 4th, dot, dot, dot. That's pretty cool. Pretty cool. Now let's take a look at it and let's try it for e to the x. Let's make another page here. And let's find the Maclaurin series. Expansion of e to the x. What we're really doing is showing a way to write as a polynomial series, a series of polynomial terms, the function e to the x, the function, if f of x is e to the x, we want to write this as an infinite series. And we're going to do that by the Maclaurin series. We can do this because the derivatives of e to the x, there's an infinite number of them. It's easy to evaluate them at 0 because we know that f of 0 is 1, f prime of 0. And here's what's really nice about this one is we know every single one of these. The derivative of e to the x is d to the x. So the derivative of the derivative is e to the x. And if the derivative e to the x is e to the 0 is 1, then every derivative is 1. So e to the x is a nice function. So this tells me that this is going to be the sum, the Maclaurin series, of for n equals 0 to infinity of the derivative, the nth derivative times x to the n over n factorial. So in this case, this is going to be f of 0, remember when n equals 0, that's just no derivative at all, plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial. And of course, this pattern continues, but all of these derivatives are 1. F of 0 is 1, so this becomes 1 plus 1 plus x, plus 1x. I keep forgetting that. Plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus this just keeps getting, the pattern continues. So basically, the sum of all, we can say that e to the x is equal to the series n equals 0 to infinity of x to the nth power over n factorial. X to the 0 power is 0. Nth factorial, or 0 factorial is 1. X to the first power is x over 1 factorial, that's 1. X to the second power over 2 factorial, 3. But that is equivalent, this infinite series is equivalent to e to the x. This allows us to approximate values of e to the x. This is a series that converges. We could show that by the ratio test, I'm sure. I'll show you that this series here converges. We may have already done this, I'm not sure. But let's look at the n plus 1 over the nth term. And so if we look at this, for any value of x, in here, for any value of x, then if a sub n is equal to x to the n over n factorial, then the ratio test says that the limit as n goes to infinity of the n plus first, so x to the n plus 1 over n plus 1 factorial would be the n plus first term, a sub n plus 1, over a sub n is x to the n over n factorial. We're looking for the absolute value. If that equals some finite number less than 1, then we're going to know that this series converges. And so we can rearrange that and say that's equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. Then we invert and multiply and get n factorial in the numerator and x to the n in the denominator. That limit is going to equal the limit as n goes to infinity of, this is going to cancel x to the x in the numerator, and this is going to be n plus 1 times n factorial, so the n factorials cancel and give me n plus 1. So as x is fixed for any value x, as n goes to infinity, this term goes to 0. So by the ratio test, this series converges, and it converges to the value of e to the x for any x value, which is really pretty cool. So the series expansion, we say, Maclaurin series expansion of e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and just keeps on going. That's pretty neat that that infinite series is equivalent to e to the x. This means if you take the derivative of that series expansion, that's equal to the derivative of e to the x. It'll give you the exact same thing. Let's look at that because we know the derivative of e to the x. So e to the x is the derivative of this. If we take the derivative of e to the x with respect to x, derivative of 1 is 0, derivative of x is 1, derivative of x squared over 2 factorial, that's going to be 2 times x over 2 factorial. That's definitely x. 3 times x over 3 factorial is going to give me x squared over 2 factorial. And then it would keep going. 4x to the 4th over 4 factorial would end up giving me x cubed when I took the derivative. Over 3 factorial. And this would just continue going. So you can see even with this series expansion, take the derivative of e to the x, you get the e to the x, the same thing. This is really awesome. This Maclaurin series. Now let's go ahead and do cosine x. Let's take a look at this. If we have f of x equals cosine x and we want to find the series expansion, we need to find f of 0. We need to find f prime of 0, the Maclaurin series expansion, right? F double prime of 0. Let's go ahead and do f triple prime of 0. We can find as many as we want, but we want to establish a pattern. We know that f of 0 is 1. Cosine 0 is 1. F prime of cosine x is negative sine x. And we know that negative sine x is 0, or is negative sine 0, f prime of 0. Sine is 0. Then f double prime of x is going to be negative cosine x. Cosine of 0 again is 1, so this becomes negative 1. F triple prime of x. Now, derivative of cosine x is negative sine x, so negative cosine x is going to be positive sine x. Evaluated at 0 again is 0. All right, let's take a look and see if this continues. The fourth derivative, evaluated at 0, is going to be cosine x. And we know cosine x is 1. This is starting to look like it may do something. Let's go ahead and verify. Let's go ahead and do the fifth and sixth derivative and see if this pattern continues. The fifth derivative is going to be negative sine x again. And we can see now we've started into a pattern. This is going to continue so that this is going to be the same as the first derivative, which was 0. And this is going to be the same as the second derivative, which was negative 1. And so we can see that these terms. So what we're looking at now is f of x. If we do the Maclaurin series expansion, this is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed over 3 factorial plus f, the fourth derivative of x evaluated at 0 times x to the fourth, well, that's x to the fourth, over 4 factorial plus the fifth derivative evaluated at 0 times x to the fifth over 5 factorial plus the sixth derivative evaluated at 0 times x to the sixth over 6 factorial plus dot, dot, dot. Let's look and see what happens here. What this gives us is f of x equals cosine x is equal to the series expansion. F of 0 was 1. F prime of 0 is 0, so 0 times x is just 0. F double prime of 0 was negative 1, so this is going to be minus 1 times x squared over 2 factorial. F triple prime of x was 0 again, so this is going to be 0 times x cubed. Go ahead and put this x here, over 3 factorial. And then the fourth derivative was 1 again, so this is going to be plus 1 times x to the fourth over 4 factorial. Fifth derivative was 0, so we end up with 0 times x to the fifth over 5 factorial. And then the sixth derivative was negative 1 again, so that's going to be minus. Let's do that, minus 1 times x to the 6th over 6 factorial. This pattern just continues, but all of the odd powers of x are multiplied by 0, so they're gone. So this is equal to 1 minus x squared over 2 factorial, and then plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial. This pattern would continue, and we would do plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, and this would just continue on forever. That's the series expansion, the Maclaurin series expansion for f of x equals cosine x. You can similarly do one. I'm going to leave it for you to do the Maclaurin series expansion for f of x equals sine x, because these are really, really important series that we encounter and see often. They're going to lead to some really, really, really cool results, including what I'll show you when we get back to class. This is going to help us to see one of the things you may or may not have encountered before, that e to the I theta is going to equal cosine theta plus I times sine theta, which is going to allow us to later on solve some second order differential equations when you get into some more interesting differential equations courses, maybe some Cal 3. But anyway, that allows us, that identity right there called Euler's formula allows us to solve some differential equations, real world phenomena, using imaginary numbers. And it's pretty cool. It's the first place that I ever encountered where you could actually use imaginary numbers to solve real world problems. It's pretty cool. And it all stems from and comes from this Maclaurin series, which comes from the Taylor series, which is Cal 2. It's just awesome. Anyway, y'all have a great Easter.